Question number 22 says compound X can be converted into compound Y in a single step. What could be the identity of X? So you could answer this question by using your basic knowledge of aldehydes, ketones, primary, secondary alcohols, and their oxidation. However, there is a specific name for this reaction. It's called ozonolysis, or if I go about it slowly, ozonolysis, right? We're talking about the ozone as in the O3, which is found in the upper layers of the stratosphere, naturally in the Earth's atmosphere. So ozone, that is O3, along with a specific catalyst like a dimethyl sulfide or dimethyl sulfur, can be used to carry out these reactions. However, you should not know that by that name. You could still use the underlying knowledge of your, like I said, primary, secondary alcohols, then ketones and aldehydes to get through it. However, questions like these do offer you an opportunity to develop new ways of thinking about compounds you're familiar with. Sometimes you don't just get the answer right away, even if you have properly memorized your chemical reactions and conditions for organic chemistry. And that is where the past paper practice comes to help. Because the more of these questions you're exposed to, the more you develop these new ways of thinking and it becomes part of your toolkit. And more of what you've done will resonate with your final exam and you'll be able to pick out the right answers more easily. That's the whole point here. So the thing is, when you encounter a situation like this, you don't go back to the textbook or the lecture notes again. If you know the concept, fair enough. You just use the question itself as a learning opportunity and develop new ways of thinking. That's how you get better. So I'll show you how ozonolysis plays out specifically as well, so that if they were to give future versions of such a question again, you kind of have a more theoretical background about that. But here is how you will pick out the answer if you were not aware of this reaction by name. First of all, notice that there are 1, 2, 3, 4, 5, 6, 7 carbons around. If you look at C and D, 1, 2, 3, 4, 5, 6, 7, 8 carbons doesn't cut it. Delete C and D because the number of carbons don't match what you're trying to create in Y. 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7 carbons in A and B, they match. Then I want you to pay attention to the fact that if you look at the double bond where the reaction is actually going to play out, both A and B contain a branch, an alkyl group connected to the bottom left carbon. The only difference is this other alkyl group. Now, if you look at compound Y, right where the carboxylic acid is found, the carbon right next to it contains an alkyl group. Now, if you look at option A and focus on the carbon on the bottom right, we can expect this one to convert into the carboxylic acid group because this is the one that contains a single hydrogen and is likely a contender to be oxidized into, let's say, a primary alcohol, aldehyde, and then ultimately carboxylic acid, right? Full oxidation. The carbon on the left contains an alkyl group and is a more likely contender of a ketone. So if you focus on the carbon on the bottom right as a contender to convert into a carboxylic acid, then the carbon right above it should be having the alkyl group because in the compound Y, the carbon right adjacent to the one containing the carboxylic acid group contains an alkyl group. So if the bottom right carbon in A is the one where the carboxylic acid group will appear, then the carbon right above it, right adjacent to it, has that alkyl group meeting our requirement. But in compound B, look at the bottom right. If the carbon on the bottom right is going to convert into the carboxylic acid group, then the carbon right above it doesn't have an alkyl group, right? So it doesn't match the composition of compound Y, based upon which you can choose option A as your answer. Yes, you do need to know that the carbons on the double bond are the ones that are going to play a part in the reaction here. That's something you have to know. So your knowledge of alkenes, primary and secondary alcohols, aldehydes, ketones, and their oxidation, that's the trick here. So on the basis of all of that, you choose option A. But like I said, there's a name for this reaction. Ozonolysis, you can remember that like this. So you have ozone plus dimethyl sulfur or sulfide reacting with a ring compound, cyclic alkene. Carbon 1 and carbon 2 along the double bond are where the reaction will happen. What you have to know is that the compound converts into a non-cyclic version, a chain version from a cyclic version. The question then arises that, could they test this type of a question again? If so, what could be the variations? So to be on the safer side, I'll tell you the variations of the ozonolysis reaction, which you can keep in mind. And if they've tested the ring version of it with the cyclic alkenes unfolding into a chain, who knows, they could test other angles too. So there's no harm in knowing that. Here is one version of it. This is where you have a carbon-carbon double bond. It's not an alkene where you have a cyclic version. It's just a straight chain alkene. 2 carbons involved. So you've got basically dimethyl sulfide and ozone, right? The dimethyl sulfide is rather acting as a reducing agent. Sometimes zinc can also play a role, but I don't think they'll ever ask you that. What you need to have our focus on is that in this kind of a setup, you'll expect 2 carbonyl groups to be created. The single hydrogen and whatever is the alkyl group R1, R2 will be retained. So that's one version of it. Another version is where you've got 2 carbons with a double bond with 1 carbon containing at least a single hydrogen. In that case, the carbon containing a single hydrogen, that side should go on to convert into an aldehyde. The other one will convert into a ketone fragment. The third version is the one tested over here, cyclic alkene. And the fourth and final version is where they show a chain with multiple alkene double bonds. Such a scenario will split up into different fragments. There will of course be a carbonyl group created along with the single hydrogen, right? Along with that, there will be a shorter fragment created where the carbonyl group and a single hydrogen, which should technically speaking be a technically aldehyde and a ketone group, right? So there could be these smaller fragments created as the chain breaks up. There could also be this one main fragment where the carbon-oxygen double bond has created. So technically speaking, it could be created where this alkyl group is attached, where I'm pointing right now, the carbon-oxygen double bond, and then on the far left. So these 3 different variations, for instance, could be there. So as a general rule of thumb, what I would really want you to pay attention to would be that, because even if you look at this question, they're not expecting you to know ozonolysis. What they're expecting you to know is that, see, are you counting the carbons correctly? Because in C and D, there is 1 more carbon than in compound Y. Secondly, are you paying attention to where the side group is supposed to be in compound Y relative to compound X? That's all that they tested. So once you know how to think like that, you can answer these questions easily. But that does require doing them. Like, no matter how solidly somebody has prepared chemistry from the textbook or from the lecture notes, if that's all they've done and they go to the exam and the exam is the first time they're attempting a question from the paper and they've done no past papers, of course they're going to struggle. Because doing these questions and developing new ways of thinking, that's part of the